Welcome back, students. We'll start this video by doing an example problem, example 5.8 in your textbook. Let me read the problem and we will go on to do the problem. The Earth's magnetic field at the equator is approximately 0.4 Gauss. Estimate the Earth's dipole moment. Okay, so how do we do this? Let me draw the Earth. Okay, the Earth is like this. Okay, and let's assume that I have a magnet at the very center. Okay, there's a magnet I have at the very center. Now, so this would be this is what I will call as a north magnetic field, a north magnetic pole, and this is the south magnetic pole. But we know that what you call as north magnetic pole is actually the south magnetic pole, and what you call as south magnetic pole is the north magnetic pole. So the magnetic field lines will be in this direction. So it's like this. It will go from here to there. So this is like a dipole, okay, and the magnetic dipole will set its own magnetic field at different points in space. And you know that if you want to find the magnetic field along the axial line, then that is, you have one equation for it. We derived that equation, and there is also another equation for the magnetic field at a point in the equatorial plane. So that is given by, let's say I will take this point, which is on the equator. Okay, so B here is equal to mu naught by 4 pi into m, which is the magnetic moment, by r cube. So this is the expression. So we've already come across that. So what we've done is that assume that there is a magnet here, and like you're finding the magnetic field at a far off a point which is on the equator, and this is the expression for it. We have already come across this. Okay. So what is the value of B? The value of B is 0.4 Gauss. So that is equal to 0.4 into 10 power minus 4 Tesla. So mu naught is 4 pi into 10 to the power minus 7, and this is 4 pi again, and multiplied by m. So divided by r cube is 6.4 into 10 power 6 meters, because it's 6,400 kilometers the radius, so that would be 6.4 10 power 6 meters, the whole cube. That's what you get here. So from this I can find m, and as a first step let me cancel these things, the common quantities. 10 power minus 4 will be gone, so I'll get to minus 3 here, 10 power minus 3. So m is going to be equal to 0.4 into, if I bring this there, it's going to be 6.4 whole cube into 10 power 6, the whole cube will give me 10 power 18 into this 10 power minus 3 here, so I can take it down 10 power 3, and when it comes here it will be 10 power 3 again. So that gives me 0.4 into 6.4 the whole cube into 10 to the power 21. So if I multiply these terms, then I'm going to get some 1.05 into 10 power 23 ampere meter squared approximately. So that is my magnetic dipole moment. This is what I have estimated. I call this as estimated value because I made some assumptions, and based on those assumptions I'm using this formula to calculate it. Okay. If you look for the value of the magnetic moment in the textbooks on geomagnetism, they give you this as the actual value. Okay? The actual value of the magnetic moment of the Earth is equal to 8 into 10 to the power 22 ampere meter square. So that is actually 0.8 into 10 to the power 23 ampere meter square. So this is 1 into 10 power 23 ampere meter square, the thing that you estimated. But the actual value is 0.8 into 10 power 23 ampere meter square. So you are very close. You are approximately right. So your error is about only 20%. So what is actually 0.8? We have estimated to be 1. So you are very nearly there. So this assumption is fairly good. Hope this is clear to you. The next thing that we talk about is magnetization. Let me take this magnet. Okay, this magnet will have its own magnetic moment M. And why does that happen? Why do you have the magnetic moment? It's because this is a magnet. It produces a magnetic field. And the strength of the magnetic field is governed by the magnetic moment and also the distance. But if you forget the distance, then it depends on the magnetic moment of this magnet. How do you make this? First I'll take an iron, a piece, and then I wind a wire around it. Okay, the iron piece is not a magnet to start with. I wind a wire around it. Then I pass current through that wire. And when current passes through that wire, and the iron piece will get magnetized. Why does it even happen? Because we already discussed that the electrons which are orbiting the nucleus, they behave like a magnet. Each atom has its own magnetic moment. But then, because of a thermal agitation, you may not get a net magnetic field outside. If I bring a magnetic field and if I subject this piece to that magnetic field, then these atomic magnets may align with the field. It depends on how strong the field that you produce and what is the current that you are going to pass through the coil and all that. Okay, suppose like I've magnetized this. Okay, I've taken this, then I have a coil, then I pass a certain amount of current, and for that amount of current there will be a certain amount of magnetic field set by that coil, and the atoms or in this piece will align with that magnetic field. If it is strong, more atoms will align. The applied magnetic field is strong, then the more atoms will align. If the applied magnetic field is not that strong, let's say I pass less current now, then a less number of atoms will align with this. The magnetic field produced by this atom after aligning will also be weak. But if I pass very high current through this coil, then more and more atoms will get aligned with the magnetic field. So it becomes bigger and bigger and bigger. So this piece, it can be a strong magnet or a weak magnet, depending on how I have magnetized this piece. Okay. Then how do you get that measure? How much you have magnetized? So that measure is given by magnetization. So I take a magnet, I take a piece and I calculate the magnetic moment of that magnet. So I get some M, and then I'm now going to divide that by the volume of that magnet. So that gives me a measure of the magnetization. It's like a certain amount of magnetic moment can be given by a larger volume too, right? I can have a larger volume, and that can also give me the same magnetic moment. A longer piece can give me the same magnetic moment. But then I have not magnetized it well. So the higher the magnetization, then you will get a certain amount of magnetic moment for the smaller volume. Okay. If the volume is smaller, if the magnetization is greater, then the magnetic moment will be great. If the volume is big and it gives the same magnetic moment as this one, then the magnetization of that piece is small, and that is what we define as magnetization. So what is magnetization? Magnetization is denoted by capital M. It's again a vector quantity, and this is equal to the magnetic moment of that magnet, so divided by volume. So if there are two pieces, a small piece and a big piece, and if both of them have the same magnetic dipole moment, then the smaller magnet that has had the greater magnetization, because for a smaller volume it is able to produce the same magnetic dipole moment. So this has been magnetized strongly. So the magnetization is greater here for a smaller magnet with the same magnetic dipole moment. So I want you to understand this. And if you understand this, then we'll go on to do a little bit of derivation. Okay, so I have this coil. Like a solenoid. And now if I say I send current I through this coil, okay, now it is going to set up a field B inside, right? So the field B will be set up inside. So this is going to be B. It will be set up inside the coil. Now I am going to keep a material, okay, within this. Inside this solenoid I will keep this material. Then that will get magnetized, then it will align with this field, most part. Okay. So first of all, this is I, and the field that is produced by the coil itself is B0. But because B0 is there, now this piece gets magnetized, then it puts its own magnetic field there, here. So this will have its own magnetic field because it's getting magnetized now. So this will put its own magnetic field there. So that I will call as Bm. So the blue lines are the magnetic field lines produced by this material, and then the green lines are the magnetic field lines produced by the coil. So at every point there, you will have a net field which is the sum of the fields produced by the material and also the coil. So the field inside V, okay, the field inside B, call this as B, okay, or I'll probably use a different color. Okay. This field inside B, that is actually the sum of this field in that way. So that here you say B is equal to B0 produced by the coil and Bm produced by the magnetic material, because that you are magnetizing this. Okay. But what is B naught? So B naught is actually mu naught into N to I. You know that it's a long solenoid. Then B naught, the field B naught produced by this is into mu naught N into I. Okay. Now what do you get here? Like N is the number of turns per unit length. I is the current, and then you also have got mu naught. Okay. Let me just take this out. Ni. I'm going to call Ni as H. H is equal to Ni. Why? Okay. You look at this field. B is equal to B naught plus Bm. Okay. Let me write this one. So now B is equal to B naught plus Bm. Let's see. What is B naught? B naught is mu naught Pn to I. But what about Bm? What about Bm? The Bm again depends on B naught. Why? Because the stronger the field that's going to magnetize this material, then the greater the Bm it's going to produce. Right? Okay. So if B naught is more, then Bm will also be more. So I will say that Bm is actually proportional to B naught. Okay? And then what does this? Bm can be written as I can introduce a constant of proportionality, right? So that call this as x to B naught. Psi, okay? It looks like x, but it's called as psi. So psi into B naught. That's the constant of proportionality I'm going to introduce. Because if B naught is more, the Bm will also be more. Because if you increase the magnetic field in which this material is kept, then the greater the field, the greater the magnetization would be. So Bm is proportional to B naught, and Bm is equal to psi into B naught. I call this psi as magnetic susceptibility. Susceptibility of the material. So this depends on the material. The different materials may have different susceptibilities. Some may get magnetized very quickly. Even for a very small amount of current, the magnetization could be great. And some may require a lot more current to flow through this one. Okay, so this is what it is. Now I'll take this and then put it in here. I'll then combine both and then do it here. So from this B is equal to B naught plus psi into B naught. Okay. So what is B naught? I'll take B naught out. B naught, take it out, 1 plus psi. So that's my expression, that's B. But what is B naught? B naught is said, it's B naught into Ni. We know that. We know this from previous videos. So mu naught to N I to 1 plus x psi. Okay. Now let's analyze this a bit. Do you have any control over mu naught? No. You have no control over this. Do you have any control over x, this xi? No. Because it depends on the material. If I keep one material, then I have one value. If I keep another material, I may have a different value. I have no control over this. So what can I control? Can I control this? Yeah. I can control the number of turns per unit length. Can I control the current I send? Yes, I can control that. So this Ni, which I got here, this is called as a magnetic intensity. H is magnetic intensity. It's N into A. So H is that part of this magnetism that you can control. That is in your hands. And the rest of the things are not in your hands. Given a particular material, you have no control over it. But you can control the number of turns that you are going to have for the coil, and then you also can control the amount of current you are going to flow through that coil. So you can control the magnetization this way. Okay? And this, let's see, 1 plus x. This, this is permeability of free space, and this 1 plus, I'll try it this way, mu naught to 1 plus xi. This is Ni is equal to h. You got it here. Okay? This is permeability of the free space, and this 1 plus xi I can call as the relative permeability. Like the relative permittivity in electricity, and this would be mu r. So my B is equal to mu naught to mu r to h. Okay? So the direction of h would be the direction of so easy to do. And what about the dimensions of h? If h dimension, if you see, h dimension if you take, this is n into I. So number of turns per unit length, and then I. So the you will if you were to get the unit for this is going to be ampere per meter. Ampere per meter. So that's the unit that you get for this, and I can ampere per meter. That's the unit for H. But what about the unit for M? Magnetization. Take magnetization, then that is equal to M by V. But what is the unit for M? M was ampere meter square. So this was ampere meter squared divided by V is meter cube. So meter square, this becomes ampere per meter. You see, the magnetization M and the magnetic intensity H, they have the same unit. So the magnetic field inside this solenoid can be given by this expression. Okay, this is B is equal to mu naught into H. So mu naught is the permeability of free space, and mu r is the relative permeability of the material, and then H is the magnetic field intensity. So we can express it that way. If the material was not there, then it is simply B naught is equal to mu naught into Ni. Because you put a material, then the material will respond to the applied magnetic field, and then you will have a different magnetic field inside that space. Very similar to what happened when you had a dielectric material in the case of the electrostatics. In electrostatics, you had two charges produced a field, epsilon naught, and then you brought a dielectric material and that was opposing this field, and the net field was less than the field produced by the electric field produced by the charges. We are using the same idea here. This coil will produce a field. You are putting in a material, and that material will produce a field, and the net field will be the sum of these two fields. So then you get to this equation, and in that process you see the magnetic field intensity H is equal to N into I. But in the case of electrostatics, the dielectric material was opposing the field put in by the the charges. Okay. Is it true here? Yes, it is true here, but then that is not the whole picture. See, there are three types of materials that we will be studying about. The first type, diamagnetic materials, then paramagnetic materials, and then ferromagnetic materials. Diamagnetic materials, like dielectric materials, will oppose the magnetic field. So the dielectric materials were opposing the applied electric field. Likewise, the diamagnetic materials will be opposing the applied magnetic field. So the net magnetic field in the case of the diamagnetic materials will be slightly less than B naught, because Bm will be acting in the opposite direction. And paramagnetic material, but not by much. They will only this one. The diamagnetic materials, they will reduce it a little bit, not much. A very slight reduction in the applied field will happen in the case of diamagnetic materials. But in the second type of materials, the paramagnetic materials, okay, they will enhance the field. They will put the field lines the same direction as the applied field, but not by much. They will only increase the field by a little bit, by a little amount. So in that case, in the case of paramagnetic materials, B would be greater than B naught, because now Bm will add to that. In the case of diamagnetic materials, Bm was opposing B naught, so the net B was less than B naught, the applied field. In the case of paramagnetic materials, Bm will add to B naught, because it will also put the field in the same direction as B naught. So this B will be greater than B naught, but not by much, slightly greater. Diamagnetic materials, B naught, the net B will be slightly less than B naught. Paramagnetic materials, the net B will be slightly more than B naught, but not by much. That's the slight difference. So, but then there is this third type of materials called as the ferromagnetic materials. The ferromagnetic materials, they have their field, they enhance this field very, very, very highly. So what happens is, the field that they put would be, even 1,000 times greater than this B naught. So I have B naught, which has certain amount of, so which has certain value. Now I put this ferromagnetic material, then the resulting field B will be 1,000 times more than B naught, or 900 times, 500 times, 600 times, hundreds of times more than B naught. That depends on the material. So those are the materials that we will talk about next. There is a table given in your book, table 5.3, and that is what has been reproduced here. I'm going to explain the table to you now. We said there are basically three types of materials: diamagnetic, paramagnetic, and ferromagnetic materials. And these materials when they are kept in a magnetic field, then behave in a certain way. The diamagnetic materials will oppose the applied magnetic field. So the net magnetic field inside the diamagnetic material will be less than the applied magnetic field. So diamagnetic material is similar to a dielectric material, right? So in the dielectric material too, the field value inside the material was less than the applied field. So in the diamagnetic material too, the field value, the magnetic field value will be less than the applied magnetic field. In the paramagnetic material, the field value will be more than the applied magnetic field, but only slightly. And same thing is the case with the diamagnetic material. Yeah, it reduces the field, but then it will have reduced it only by a very small amount. And then the ferromagnetic materials, or the materials that you see here as magnets, so they aid the applied magnetic field, and they aid it by a very large amount. So basically, to cover all this, we came up with a general formula, which was this: B, the magnetic field strength, was equal to mu naught mu r to h. Mu naught is a permeability of free space, and mu r is the relative permeability of the material, and h is the magnetic field intensity, that is the part of the magnetic field that you can control, n into I. So the number of turns per unit length into I, the current flowing through that coil. So this is the expression you came up with. And I can take these two things together, and then I can say that B is equal to mu to h. So now mu is the permeability of that material. So this is permeability of the free space, and this is relative permeability of the material. This is relative permeability of the material. But this one, which is equal to mu naught into mu r, is the permeability of the material. So I can write it like this: mu is equal to mu naught mu r. But what we know about mu r? Mu r is actually equal to 1 plus xi, where xi is the susceptibility. Susceptibility of the material. So there are three terms here, okay? Mu r, mu, and xi. They are dependent on each other. They are not independent quantities. If you know one, then you can find the other two. If I know xi, then if I add 1 to that, then I will get mu r, the relative permeability. And if I know the relative permeability, then I can find mu, this. Because I know the value of mu naught, it's a constant, 4.10⁻⁷. So mu r I found from this, and now I can find mu. Or if I know mu, then I can find mu r, because I know this value, so I can easily find mu r. And if I find mu r, then I can find the susceptibility also. So these three quantities, xi, mu r, and mu, are dependent on each other, not independent quantities. If you know one, you can find the other two. Now we'll talk about this xi, mu r, and mu for the different types of materials. That is what this table is all about. Okay, let me take the diamagnetic material. I said, in the case of the diamagnetic material, the magnetic field inside that material would be less than the net magnetic field. The net magnetic field inside that material would be less than the applied magnetic field. Why? We said this. We said that B was equal to B naught plus Bm. So B naught is applied magnetic field, which was equal to mu naught into H. And then Bm, this will be opposing this field, so this will be negative quantity. So then net B will be less than B naught in the case of diamagnetic materials. Okay. So if this has to oppose, look at this. Let's take this. If the relative permeability is 1, then B naught, B will be equal to B naught straight away, because B in that case will become mu naught H, that is equal to B naught, the applied field. But B in the case of diamagnetic materials is less than B naught, which means that this has to be less than 1. So the relative permeability must be less than 1. If this has to be less than 1, then let's come here. Mu r is actually 1 plus xi. 1 is a fixed number and xi has to be a negative quantity. Only if this is negative, this can be less than 1. Only if this is less than 1, B can be less than B naught in the case of diamagnetic materials. So let's talk about these three quantities here: xi, mu r and mu. Let's take diamagnetic material. So xi has to be less than 0, it's negative quantity, and this has to be greater than or equal to minus 1. Why? If this is minus 1, then mu r becomes 0, then there will be no magnetic field here at all. It cannot be less than that. You can't have a negative magnetic field or something. Okay, so this is the lower bound for this, so minus 1. Less than or this is xi is greater than or equal to minus 1 but less than 0. So what you basically say here is that xi is a negative quantity. Okay, if this is, and you need to see, what is the value of xi then? It is not a big number. I say that it is opposing the magnetic field, but then it doesn't reduce it too much. Okay, except the case of superconductors. Superconductors are the best diamagnetic materials. They oppose the field completely, totally. The magnetic field inside the superconductor would be 0. Okay, so that is in the presence of an external magnetic field, then it is 0. So that is why you are using superconductors for levitation and then super fast trains and stuff. Like that's where we get interested in superconductors as practically usable things. Okay. Anyway, so in that case it's minus 1. In the case of superconductors, xi will be minus 1 because superconductors are the perfect diamagnetic materials. We'll talk about that later. But in the case of all the other diamagnetic materials, the magnetic susceptibility is not much. It's again 1 in 10 power 5. It's like the value would be a negative, say, 0.999 or something. Okay, 0.99. Sorry, minus 0.000001 or 2 or 3 or something like that. So this is a very small quantity. So if I add this 0.0001 to 1, then mu r is going to be 0.9999. Okay, so it's almost 1 but less than 1. So if you take mu r, it's greater than 0 or equal to greater than or equal to 0. In the case of superconductors, then it will be 0. But otherwise, it's greater than 0, and it has to be less than 1. That's what we saw. It has to be less than 1 in the case of diamagnetic materials. And what about mu? Well, since mu r is less than 1, then mu because this less than 1 has to be less than mu naught. It is going to be 0.99 mu naught. It's not mu naught, or 0.95 mu naught. It's less than mu naught. Mu naught is 1 mu naught, but 0.99 mu naught is less than 1 mu naught. So you say that mu is less than mu naught for diamagnetic materials. Let's talk about paramagnetic materials. Again, in the case of paramagnetic materials, the magnetic field inside the paramagnetic material would be greater than B naught, greater than the applied field, but not much, by a very small number. Okay? It's not going to be too great. Again, that is also which means that this is not too big. This relative permeability is not too big. It is more than 1, because the field now has to be greater than B naught, which means that mu naught has to be greater than 1, which means that this number xi, susceptibility, has to be greater than 0. If it is less than 0, this will be less than 1, but this has to be greater than 0, so that this is greater than 1, but not by much. Okay, so this is also a small number, that's why you call it a small epsilon. It's a very small number, not much, very small number, but it is greater than 0. So xi I have here is actually greater than 0 but less than a very small number. Okay? So if this is the case, then what will happen to mu r? Mu r will be greater than 1 but less than this 1 plus epsilon, small number. And mu naught is going to be less than mu naught, or mu is going to be greater than mu naught, clearly. So mu is going to be greater than mu naught. Because this is more than 1, so it could be 1.001 into mu naught is 1.001 mu naught is mu. So 1.001 mu naught is still greater than 1 mu naught. So mu is slightly greater than mu naught. Okay. And let us talk about ferromagnetic materials, the third one. In that case, these are the things that you think of when we talk about magnetism. The lodestones or the bar magnet that you see, they are all ferromagnetic materials. And they greatly enhance the applied field. Their magnetic susceptibility is huge, in hundreds, 400, 500, 1000, much greater than 1. So these are the magnets you see in the real world. So if this is much greater than 1, then mu r is going to be much greater than 1. In fact, mu r is almost equal to the susceptibility. I can ignore 1 because this is much greater. This could be 900 or 800, 400, 600. So I can easily ignore this 1. So mu r, the relative permeability in the case of ferromagnetic materials, will be approximately equal to the magnetic susceptibility, much greater. So if it's much greater, then mu r would be much greater than 1. If mu r is much greater than 1, then clearly mu will be much greater than mu naught. So 900 mu naught, 800 mu naught, 400 mu naught, 500 mu naught. See, much greater than that. So this is a table that explains the relationship among these three quantities: xi, mu r, mu. Magnetic susceptibility, relative permeability, and permeability of the material. Hope this is clear to you. Now let's do the example problem, 510. Let me read the problem. A solenoid has a core of material with relative permeability 400. the windings of the solenoid are insulated from the core and carry a current of 2 amperes. If the number of turns is 1000 per meter, then calculate A, H, which is the magnetic field intensity, B, M, which is a magnetization, C, B, the magnetic field strength, and then D is IM, which is the magnetizing current. This is something new, we'll talk about that. Magnetizing current. Okay, we'll do it one by one. Let me take the first one, A. I need to find H, the magnetic field intensity. This we know is given by the expression for the solenoid N into I. Okay, N in this case is number of turns per meter. So it's already given in the problem, which is 1000 turns per meter. So this is going to be 1000 turns per meter multiplied by I. The current flowing through the solenoid is 2. So this is that. So this is going to be equal to 2 into 10 power 3. What's the unit? It's going to be ampere per meter. Ampere per meter. Number of turns per meter, and the current I is amperes. So 2 into 10 power 3 ampere per meter. So that's the field intensity. Second one is B, but to calculate the magnetization I would require B. So I'll do C first and then I'll come to do B. Then C, I need to find B. So what is B? B is equal to mu naught mu r to H. So mu naught, 4 pi to 10 power minus 7, and mu r, the relative permeability is 400. To H, you calculate that to be 2 into 10 power 3 Tesla. Okay. So this 4, 5, right? 2 zeros and 3 zeros here. I'll take them and then I'll do just 2 here. Okay. So it's going to be minus 2. And 4 into 4, 16 into 2, 32. 32 into 3.14. So 32 into 3.14 is approximately 100. So 32 into 3.14 into 10 power minus 2. So this is going to be 100. It's going to be 1 by 100. So this is going to give me roughly 1 Tesla. Okay. Now let me come back and do B. So that's magnetization. How do you find magnetization first? Okay. I told you when we were talking about magnetization, I said magnetization and a magnetic field intensity H, they had the same unit. Okay. We are going to use that idea to get to that. Okay. What does the magnetic field B? This B is B naught plus Bm, right? So B naught is applied magnetic field with a coil, and Bm is a magnetization that is taking place in the material. Okay. So we said Bm was proportional to B naught, and that gave you Bm is equal to xi into B naught. Okay, that's what we saw. But what about B naught? So B naught is actually mu naught to H. Then what about Bm? Bm must be equal to mu naught B naught into H into xi. So this can be written as a magnetization here. Okay, so this is going to be just a comparison. So you got B naught, mu naught into H. So this also has mu naught here, then H and H, and this must not have any units. The magnetic susceptibility cannot have any units because this must have the same unit as that. For Bm, it should have the same unit as B naught. So this is what you call as the magnetization equivalent. Okay, so you say M is equal to Xi into H from this. Okay. But what is Xi? The susceptibility that comes from the relative permeability. What do you know about relative permeability? So the relative permeability is this: mu r is equal to 1 plus Xi, and mu r is given as 400 here. So I got 400 is equal to 1 plus Xi. So Xi written as 399. Okay. And what is magnetization? Very simply 399 into H. You know H and you know this. So what do you get here? So in that case, this magnetization is equal to 399 into H is 2 into 10 power 3 ampere meter. And that would give you the value of how much? Somewhere around 8, right? So it's going to be 798 is what you get. 798 into 10 power 3. So M is equal to 7.98 into 10 power 5 ampere meters. So that's the magnetization which we got here. Okay, so that is how we do B. And coming back to the magnetizing current. So what is this magnetizing current, G? That's something new. Okay, so now you have a solenoid, right? The solenoid has a core, with a material, core of a material with relative permeability 400. And then it produces this magnetic field, 1 Tesla. And what's the current flowing through it? The current that is flowing through it is just 2 amperes. Okay, the magnetizing current is defined like this. Suppose I don't have a core, I just have the solenoid only. Then, what is the amount of current I should pass to have the same field? Right now I pass a certain amount of current to produce a field with the core, which is 2 amperes. I pass 2 ampere current with the core to produce a B of 1 Tesla. But if I don't have a core, then I must be passing a different amount of current to produce the same field. Now, the magnetizing current is excess current that you pass to produce this field. That's a magnetizing current. Okay? Go this way. So now I have a core. Now I have a coil without the core. Now I should be passing a current I through this, and that should produce the same field B. Okay? Then the excess current I pass is a magnetizing current. So I in this case is actually equal to the current that I pass plus the magnetizing current. But the current I pass is 2 plus I. So this current should produce my B. So what's the B here? My B is equal to now mu naught n into this I, which is 2 plus Im. Okay, so this is the current I should be passing to have the same magnetic field. So I have 1 Tesla as a magnetic field equal to 4 pi into 10 power minus 7, and this n is actually 1000, and now I got 2 plus 9. Okay. So what would I guess now? So this will give me minus 4. Okay. So 2 plus Im is going to be equal to 2 plus Im is going to be equal to 1 divided by 4 pi. Now it's going to be 10 power minus 4 down, so it will be 10 power 4. So 10,000. Okay. So we'll get a set. So it is going to be 10,000 divided by 13 or something. Okay. So that will give you this Im. So Im is equal to, if we do all this stuff, then the magnetizing current is given as 794 amperes. So what it means is that if I don't have this core, and if I need to produce the same B, then I should be passing 794 plus 2, 796 amperes through this to produce a B of 1 Tesla. A huge amount of current would be required to produce the same amount of magnetic field strength. Okay, so having a core greatly reduces the amount of current you need to pass through the wire to produce a magnetic field of certain value. So that is the reason we use the magnetic, the core to produce a high value of magnetic field strength. Okay. If this was not there, the core was not there, then I must be sending in 794 plus 2, 796 amperes to produce B. But now I send only 2 ampere current through the coil to produce 1 Tesla. So the magnetizing current is 794 amperes. That's the idea. Hope it's clear to you.